kids from the men and South Africa as a whole. So we want you to pass physics and progress to your next level while studying work energy theorem. We will start from stating the work energy theorem because it is examinable. This is something that you already know. Please, when you state definitions and you state principles and theorems, make sure that you use the exam guidelines. You use the definitions, theorems, and principles that are according to the exam guideline. Don't just use any, even if you find it on the textbook. When you are examined, we expect you to use the exam guideline because the exam guideline, it directs us that define this as, explain this as, meaning that we need to strictly use the exam guideline. So the work energy theorem, according to the exam guideline, we are first going to write the principle mathematical. It says work net is equals to change in EK. Work net is equals to change in EK. So let me explain, write this in ways. So the work energy theorem, you just write this formula in ways. You must not leave anything. This is the change in EK. EK, which is the kinetic energy. EK represents the kinetic energy, which we usually call the energy of movement. So work energy theorem says that the work net done on an object. Notice that I never said the work done. I said the work net or the net work done. I can say the net work done if I want. The net work done or the net work done. You must not just say the work done. Here we're talking about the net work done. Why are we saying the net work done? It is because it is the work done by a net force, not just the work done by a single force. It's the work done by a net force. I will explain what I mean by a net force. So it says that the net work done on an object is equals to the object change. Notice, I'm not saying it is equals to kinetic energy. There is this delta, which represents change. So the net work done on an object is equal to the object change in kinetic energy. So notice energy. Notice that I did not just say that the work done is equal to the change in kinetic energy. That is wrong. That is not work energy theorem. Work energy theorem said that the net work done, so don't leave the word net, the net work done is equal to the object change in kinetic energy. Don't say kinetic energy. So you just take this the way it is. You just say the work net done, the net work done on an object is equal to the object change in kinetic energy. That's why here we're change in EK. So when you are stating it, do not forget the crucial ways. Okay? So you need to state it the way it is here. I know that we do not have a problem of stating theorem. So now we are going to go into details on the work energy theorem. What does the word net mean? What does the word net mean? The word net, it means that the total. Net is total. we talk about net pay, the net salary, the net gain. The word net, it means the total. The total. Okay, this is just an English explanation, not even physics. Net, it means total. But what do we mean? Why are we saying the net work done? Because you can see it is W net, which means the work net, the work net. What does it mean? There is a formula whereby we have the word net. It is not coming from for the first time. In grade 11, we also use the word net, and we're using net with F net. We say F net is equal to MA. What does it mean? What does net mean? Net, it means the total. So F net, it means total forces. Total forces acting on an object. Acting on an object. So net force is a what? The total forces acting on an object. It means it is the sum of all forces acting on an object. Is equal to the product of mass and acceleration. We know this. We know this formula. We say F net. So we are going to explore work net and F net. How are they related? Because there's this work net is influenced by the F net. So we want to explore that on what is happening. Okay. So now let me erase this and start to explain to you. Okay. Let's say, let me explain F net, which is equal to MA, product of mass and acceleration. If we can have this, and we have a box which is being pulled up, a box is being pulled up by force F on a rough surface. Rough surface. I told you in the first lesson that immediately you hear the word rough surface, it means there is friction. When you are told that it's a smooth surface, it means there is no friction. I told you. So, okay. This is what we have. This is what we have. You can see. This is a thin line which is 80 degrees. So a box is being pulled up by a constant frictional force. A box is being pulled up by a constant frictional force. So, how many forces? What are the forces that are acting on an object? We usually draw a free body diagram. We draw a free body diagram whereby we draw a straight line, then we draw a dot in the middle of the straight line, and this one becomes the applied force. This is the force which is pulling the object to move up the incline. Then the force which opposes, which pulls down the object, is going to be what? Frictional force. Notice that we don't claim that if there is a force which is being applied going up, there is friction. We have concluded that there is friction because we are told that it is a rough surface. And it doesn't mean that if an object is going up, there is always an applied force. Here there is an applied force because the box is being pulled up by this force F, and this force F is what is applied force, so that is what is happening. Then we're going to draw a straight line which is vertically down, and that is the gravitational force. Gravitational force is always downwards. Then we are going to draw a normal force which will point up. It must be perpendicular to the surface. By being perpendicular, we mean that it must form an angle of 90 degrees with the surface. So it means 90 degrees. 90 degrees is going to point this side. So this is our normal force. That is our normal force. Why did we make this normal force to point this side? It's because we want a 90 degrees here. 90 degrees, it is an angle that we have on a corner. You know, a sharp corner. That corner is 90 degrees. So that is the reason this normal force is pointing this side. If we were to make it to point up straight like this, it will create a sort of an acute angle. It's a small angle which is smaller than 90, you can see. So it has to face this side so that we can create what? 90 degrees between the surface and the normal force, because a normal force is a force which the surface exerts on an object it is contact with and act perpendicular to the surface. So you can see from this diagram the forces that are acting on this object. The forces which are acting on this object, which is being pulled up by a force F. Force F is pulling the object up, the box, of course. Here are the forces which are acting on the box: frictional force, applied force, gravitational force, normal force. So what does that mean? What does that mean? It means that the F net, it means is the sum of all the forces which are acting on an object. F net is the sum of all the forces that are acting on an object. It means that although it will depend on the direction of where the object is moving, because we know that this gravitational force may produce components parallel and horizontal. I won't explain that because I just want to explain the net force. Net force is the sum of all the forces which are acting on an object. It means the F net is the frictional force plus the applied force plus the gravitational force plus the normal force. Although some of the forces will have a magnitude of 0, I'm not interested in that. I'm interested in explaining to you to know that a net force is the sum of all the forces that are acting on an object. So you can see F net is equals to frictional force, applied force, gravitational force, normal force. Why did I say I add these four forces? Because these four forces are the forces which are acting on this box as it moves up. I hope you have grabbed what F net means. F net, it means the sum of all forces acting on an object. F net is the sum of all forces that are acting on an object. That is F net. F net is the sum of all the forces that are acting on an object. I hope you understood that. Okay, sometimes you can find that F net, it is only, F net can be equals to gravitational force. For example, F net can be equals to a frictional force. F net is the sum of all the forces acting on an object. It means that if there is only one force acting on an object, it means F net is equals to that only one force acting on an object, because F net is the sum of all the forces that are acting on an object. Let me give you another example while I'm explaining what F net is, so that we can go and explain work net, because work net is coming about F net. Okay, look at this. Here's a smooth surface. I'm saying that the surface is smooth, right? The surface is smooth. Here is the smooth surface and there is a box there. The box, this box, it was dropped. Here is point A, this is point B. Box is dropped at A. Meaning that someone came with a box and he left that box at A. When you leave this box at A, the box is going to do what? Is going to move down the incline. Notice that the surface at which the box is moving, it's a what? It's a smooth surface. The second thing to notice is that there is no applied force because the box is being dropped here. The box is moving on its own. There is no force which is applied, which is causing the box to move. Notice that the things that I'm saying, there are not assumptions. You will be given information in the question. You will be told that the force is being applied to cause the box to move. Or you will be told that the box is moving from point A to B. You will be told if it's a smooth surface or if it's a rough surface. And if you are given a real situation like they are talking about a car, sometimes they may not tell you if it's a rough surface or a smooth surface. But you as a person who is doing physics, you need to know that a car will move on a road. All the roads are rough. Whether it's tar road or gravel road, all the roads are rough. So you will know that there is friction. Whenever a car is moving, a car will be moving on a rough surface. There is no way a car can move in a surface which is not rough. So you need to notice side things whenever you are not told about the surface, but they are talking about a car. Because this physics that we are teaching you is a real thing. So you will need to know that if it is a car, there is friction. Okay. So the box is moving on its own on a what? On a smooth surface. Let us draw a free body diagram. A free body diagram is very important because it tells us about the forces which are acting on an object. The free body diagram for this one, how are we going to do it? We are going to draw a dot, then we do what? Draw a straight line, and that is gravitational force. That is gravitational force. And then we're going to have what? The normal force. Normal force, which will be in this direction. Why is normal force pointing this direction? It's because the incline is like this. You can see that the incline is like this. Meaning that if I want to create 90 degrees, the 90 degrees must be like this to form what? A corner. You can see that's why the normal force is pointing this side using this hand. You can see, right? If the incline was like this, if the normal force using this hand, it was going to point. That's why the normal force is pointing this side. Can you see? Is the object being pulled by a force? Is there a force which is being applied on the box to cause it to move down? No, there is no such force. Is there a frictional force which is opposing the motion of direction of the box? No, there is no friction, it's a smooth surface. Meaning that the free body diagram for this box, it is this one. Here is the free body diagram of that box. How many forces do we have which are acting on an object? We only have two forces. Although I know that we're going to have one force, normal force, which will have the magnitude of 0. I'm not interested in that. I'm just teaching you what F net is. F net is the sum of all the forces that are acting on an object. It means that F net, how many forces are acting on an object? F net is equals to gravitational force plus what? Plus normal force. Why am I saying F net is equals to gravitational force and normal force? That is all because that the only forces which are acting on this object is gravitational force and normal force. And F net is the sum of all the forces that are acting on an object. So we're going to have this. I know that we're going to have a magnitude of 0 for some of the forces, but the truth is F net is the sum of all the forces that are acting on an object. That is F net. You can see that on this object, only two forces are acting. It means that our F net is equal to the sum of normal force and gravitational force in this case. So you need to notice that you must not claim what F net is. F net is the sum of all the forces that are acting on an object. Okay, so now we are going to go to the work energy theorem. The work energy theorem which states that work net is equal to change in EK. Change in EK. Okay, so how do we solve that one? It is called wet net because it's the wet net. What is wet net? Wet net is the work done by a net force. Wet net is the work done by a what? A net force. What is a net force? A net force is what? Sum of all forces acting on an object. Sum of all forces that are acting on an object. So you need to notice that wet net, it is the what? It is the work done by a net force, meaning that you can use energy theorem to calculate the net work. You can use energy theorem to calculate the net force. You can use the energy theorem to calculate the what? The net force. Because work net, it is the work done by a net force. What is a net force? Is the sum of all forces acting on an object. Okay, let me move into more details. On work net. What is happening with work net? We know a formula which says that F net is equals to product of mass and acceleration. These two formula, the work energy theorem and the F net, they are related. Because work net is the work done by this force, this net force. And what does it mean? We know that work is equals to the force. What is the force? Is the net force this time. Multiplied by what? Multiplied by the displacement. Multiplied by cos theta. So work net is equals to what? F net multiplied by the displacement multiplied by cos theta. You know that work is the product of the force and the displacement of an object. That is when we multiply the force which is acting on an object and the distance that force caused an object to move, that is the work done. So this time we're not just talking about the work done by one single force. We're talking about the work done by all the forces acting on an object. That's what work net is. Meaning that we can be able to relate this formula of work net, as I'm showing you, that work net is equal to the work done by the F net. What is F net? F net is the sum of all the forces which are acting on an object. You understand? So it means we can relate this formula and this formula. What can we say? We can say work net is equals to product of mass and acceleration. We multiply by displacement, then we have cos theta. You see, we can we can calculate the acceleration, by the way. We can calculate the acceleration using the work energy theorem. Sometimes it is examinable whereby you need to calculate the acceleration using the what? The work energy theorem. Because F net is the product of mass of an object and the acceleration. And the work net is the work done by the F net, so we can relate this. I'm just passing through here so that you can understand, because sometimes we leave without teaching you this, so that you know that the two are related. Okay, so let me break this. I'm still explaining what work net is. Work net is the work done by all the forces acting on an object. Let's say I have an object. Here's my object. This is 20 degrees. We have a rough surface. This surface is rough. An object is moving on a what? On a rough surface. Where's the object? Then we put the object here. The object is going down, it's going up. The object is going up, it is now up. From point B and A. The object is moving up. The object is moving up. Object is moving up, and there is a applied force. There is force F, which is causing an object to move on a rough surface. Let us draw a free body diagram for this one. Let us draw a free body diagram. Our free body diagram, we're going to have a dot, then we draw. Then what will we have? We're going to have applied force. Then we're going to have frictional force, which is pulling an object down. It's pulling an object down as the object is moving up. Then we're going to draw a straight line, which is vertically down F, G. Then if we want to draw the normal force, we're going to have a line which will face that direction. The direction where I'm standing causes me to draw something which is wrong. Yeah, it's going to be like that. Gravitational force, then normal force, normal force. Notice that I didn't cram that the way I must draw a free body diagram, I just draw anyhow. Because I know how these forces behave. Gravitational force is always downward. You draw a line which is vertically downward. Normal force, you draw a line which will be perpendicular to this surface. I'm talking about where the object is moving. So that will be normal force will form 90 degrees with that surface. So that's why you see my normal force pointing that direction. I didn't just grant that, I need to make it point in that direction. So please make sure you understand. I think I've repeated that many times. Okay. So now let us talk about wet net. We want to calculate the wet net on this object. The wet net on this box, the object is a box. What is wet net? We can first talk about F net. What is F net? F net is the sum of all forces acting on an object. We've got applied force, we've got frictional force, we've got gravitational force, we've got normal force. Although I know that the sum of, the normal force will be 0. The normal force I know will be 0. But I need to write it. It is also a force. 0 is a number. 0 is a number. So I have got these 4 forces acting on this object as it moves up. This is the F net. So what does it mean? What does it mean when we explain that in terms of wet net? It means that wet net is the sum of the work done by all the forces. It means I'm going to say work done by frictional force, right? Plus work done by applied force, plus work done by gravitational force. I know from lesson number 2 that normal force is going to do 0 work. Why is it that normal force is doing 0 work? Forces which end perpendicular to the surface do 0 work. If a force is perpendicular to the displacement, not the surface to be precise. Forces which are perpendicular to the displacement, they do no work, they do 0 work. Forces which are perpendicular to the direction of displacement, they do 0 work. So I'm not going to waste my time in calculating work done by normal force because I know I'm going to get 0. So it means that is work net. That is work net. It means work net is the what? How many forces? Actually, let me remove the normal force even here because I know it will be 0. So what does F net mean? It means F net is the sum of all the forces acting on an object. What about work net? Work net is the sum of the work of all the forces acting on an object. It means that work net is going to be work done by applied force, work done by frictional force, work done by gravitational force. That's why work net, we're going to have work done by frictional force plus work done by applied force plus work done by gravitational force. Why did I write these three forces? Because these forces are the ones which are acting on that box. And since they are acting on that box, they are the ones which are doing work on that box. Meaning, since I have three forces which are doing work on that box, if I want to calculate the work net, I'm going to add the sum of the work which is done by all the forces that are acting on an object. So work net is the sum of all the forces that are acting on an object. Work net is going to be the work done by frictional force, work done by applied force, work done by gravitational force. Sometimes you will find that the work net is only equals to two forces. The work net is only equals to one force. Why? It's because the only force acting on an object is that given force, so it is bound to be equivalent to the work net. Okay, let me just give you another way explanation. Let me give you another explanation. Okay. Today is the 1st of September. 1st of September, 9:30. It's my free time at work. So I'm recording this lesson during my free time. I know we are writing next week paper 1 on Friday, on the 8th. You are writing your trial exam. So yeah, I am with you. It is 2023. Those who will watch this video in 2024 or 2025. Okay, let us move forward. Let's say I have a smooth surface. A smooth surface. Can you see? Here's a smooth surface, which is 10 degrees. Can you see? An object is moving down. An object is moving down on a smooth surface. Object moves on its own. The object is moving on its own. Let us draw a free body diagram to indicate the forces which are acting on this object. We're going to draw a dot. It's a free body diagram, a dot. The box is represented by a dot. Then we draw a gravitational force. We draw a straight line which is vertical down Fg all the time. Gravitational force is always downward, and it acts on everything. Gravitational force acts on everything. It is always there. That is the gravitational force. Then, what do? We want to calculate not to calculate, to draw a free body diagram. It's a smooth surface. It means there is no frictional force. The box is moving on its own. The box is moving on its own, meaning that there is no applied force. Normal force is always there because it is the force which the surface exerts on an object, and this object is on a surface. So normal force is bound to be there. And notice, don't cram that on each and every object there is normal force. Normal force depends on the surface. If the object is put on a particular surface, then there is normal force. But if an object is not on a surface, just like this marker, it is not on the surface, then there is no normal force. But gravitational force is always there. Gravitational force is on all the objects. Remember, gravitational force is a force which pulls object toward the center of the universe. So it is always acting on all the objects on Earth. Okay, so we're going to have our own gravitational force, which will be like that. Okay, our normal force like that. Gravitational force is this one. Why am I drawing this line to point this direction? Is because if you have a line pointing this direction, and you see this direction, it means you will do what? You will create an angle which is 90 degrees to the surface. So the normal force must create an angle of 90 degrees. Angle of 90 degrees is a corner, a sharp corner. corner of a textbook, corner of a house, the angle that is there is 90 degrees. So that's why my normal force is pointing on this direction. Okay, I hope I have taught you to draw every body diagram. By now you are able to draw. You know that you don't cram the things that you do. Okay, I'm explaining what work net is. How many forces are acting on an object? We have got two forces, normal force and gravitational force. Will normal force do work? No, normal force does not do any work. Why? Because forces which are perpendicular to the direction of displacement do not do work. So it means how many forces are doing work here? It is only gravitational force. Then, what is work net? Work net is the work done by all forces that are acting on an object. How many forces are acting on this object which can do work? Only one force. Why am I saying only one force? There is only gravitational force which can do work. Normal force cannot do work because it is perpendicular to the direction of displacement. It means work net is equal to the work done by gravitational force. You don't claim that work net is equal to the work done by gravitational force. There is no formula which says this. It differs with scenarios. Why am I saying work net is equal to the work done by gravitational force? It's because there is only gravitational force which can do work on this object. As we know that normal force cannot do work. There is only gravitational force which is acting on this object which can do work. So that's why I'm saying the work net is equal to the work done by gravitational force, because work net is the what? The sum of all the forces that are acting on an object that are doing work. The sum of the work done by all the forces that are acting on an object. So it means work net is equal to the work done by gravitational force. And I hope you understand what work net is. I hope you understand. I'm going to give you a puzzle by working out a question with you to make you understand the work energy theorem even more. So the work net is the work done by all the forces that are acting on an object. Okay. So now work energy theorem states that work net is equal to change in EK, whereby work net is equal to 1/2 LVF squared minus 1/2 LVI squared. You understand, right? The main important thing to understand is the work net. Work net is the sum of all the forces that are acting on an object that are doing work. Sum of all the forces that are acting on an object that are doing work. Okay, let's say I give you this scenario. Here's the scenario. Can you see that? You can see. Then this is the surface. Let's say where's the surface? Like this. Here's the surface. Can you see the surface? Then and it's rough. It's rough. It's a rough surface. Then with A, with B. Here's a box. Here's a box A, B. No, let us A, B, C. They say a box is pulled from point A to B. From A to B is smooth. The word smooth, it means that there is no frictional force. So a box is pushed from A to B, then it moves on its own from B to C. Do you understand what is happening? A box is being pulled from what? From A to B, then it moves on its own from B to C. Meaning that a force was applied here at A, whereby a box was what? Was pushed. Then when it was pushed, then it later on moved on its own from B to A. You need to notice, I know that most of you think that when object moves it's because there is applied force. Have you never seen a car move on its own? You find that you start an engine, then when you come to a particular place you switch it off. There is no applied force because the engine is not working, but the wheels of a car, they are moving. There is no applied force, but a car is moving. You understand? So do not claim that because an object is moving, it means that there is applied force, you need to read and understand what is happening. Here is a box is pushed from what? From A to B, then it moves on its own from B to C. It means there is no applied force. Okay, so let us draw a free body diagram for this scenario. Here's a free body diagram. We draw a dot. One, FG, a line which is vertically down. A line which is vertically down. Then normal force, because an object is on the surface, Fn. We're told that it's a rough surface. So since it's a rough surface, it means there is what? There is frictional force. The question is there applied force? No, there is no applied force. There is no force which is causing this object to move up. So it means these are the only forces which are acting on the object. These are the only forces which are acting on this object when it is here. Since it is the same box, I told you that the box was pushed from A to B, then from B to C, it moved on its own. It was pushed, then from B to C, it moved on its own. So what does it mean? It means there's no applied force from B to C. So here's the free body diagram from B to C. From B to C, the object moved on its own. So this is the free body diagram. This is the surface. You can see the normal force is 90 degrees, is perpendicular to the surface, then we have a gravitational force. Then, what do we do to this? How do we explain this? What do we do? And how do we explain this into details? Okay, so this is how we do. Let us explain work net for this scenario. How many forces are acting on an object which can do work? Gravitational force and frictional force. We know normal force will not do work because it is what? It is acting at an angle of 90 degrees to the surface of an object. We're good, right? So we're going to have the what? The frictional force and the gravitational force. Frictional force and the gravitational force, these are the forces which will what? Will do work. So it means the work net is equals to what? In this scenario, you don't cram these formulas. It depends on the scenario. Work net is equals to the work done by frictional force plus the work done by gravitational force. Why am I doing this? Because these are the forces which are acting on an object, and they are the only forces which can do what? Which can do work. These are the only forces which can do work. So I hope you are understanding what is going on. I hope you are understanding what is going on. I hope you understood what the work energy. 3 meters above the horizontal at point R. You can see the question that is appearing on your screen. So we are going to take 2.1, which reads as the frictional force, a non-conservative force between the surface and the block is 18 Newton. And we know that from the starting point to point P until point Q, there is no friction. How do we know? It's because they say a smooth surface. I already told you that the word smooth surface, it means that there is no friction. So now we need to do that question. Let us start. 2.1. Use energy principle only to calculate the speed of the block at point P. I'm happy that if you are following this lesson, I have been explained about the conservation of energy and other principles. They will be done in lesson number 4. After this lesson, if you are interested and you are understanding me, you are going to watch the next lesson after this one, which will be focusing on the energy, the principle of conservation of energy. Then we will be reaching the end of the work energy theorem. Then we do power and we are done. Let us do 2.1. 2.1 he says that use energy principle only to calculate the speed of the block at point P. Whenever they say that energy principles, whenever they talk about energy principles, they are talking about all the things that we are doing in work energy theorem. In the work energy and power. All those formulas of work energy and power is what we call energy principles. Sometimes I used to have a problem. I used to think that when they say energy principles, they want you to use the energy conservation of mechanical energy and everything. So energy principles is what we are doing in this topic called the work energy theorem. Everything that we do in this topic is the energy principles. So you can use the work energy theorem, you can use the conservation of mechanical energy, which I will teach or touch on these videos. Okay, so let us start. And myself, I'm going to use the work energy theorem. The work energy theorem will say that work net is supposed to change in EK. The question wants us to calculate the speed of the block at point P, meaning that we're going to look at the start where that 5 kg block is up until point P. So I'm going to use the work energy theorem. And remember, for writing the formula, you get a mark. But the mistake that you should not make is when you don't know how to solve something, you write the formula and you leave it like that. You will forfeit a mark. A mark is only awarded when there is a formula with substitution. Even if the substitution may be wrong, you get the mark for a formula. But if you write the formula without trying to substitute, you're going to get it wrong. So whenever you don't know what to do, write the formula and try to work on it, try to substitute something. Then if it is wrong, you're going to get the mark for a formula. You get the mark for a formula if there is substitution, whether it is correct or incorrect. Okay. We can draw that object. It is here. It is 5 kg. Right? We are being told. What is it that we are told? We are told that it's a smooth surface from point start to point P. It's a smooth surface. Let us draw a free body diagram. Notice that you do not need to draw a free body diagram when you are answering the question. I'm just drawing it because I'm teaching you. I want you to understand. So, if I want to draw a free body diagram for this, I'm going to have a dot. I'm going to have gravitational force, which is a force which is going to point down. Then I must have normal force. My normal force is going to point in this direction. Normal force. Why is pointing in direction? So that it can create a 90 degrees. A 90 degrees with the what? With the surface. You can create a 90 degrees with the surface of an object. So my free body diagram is going to look like this. Do I have frictional force? No. They said it's a smooth surface. Do I have applied force? No. The object is moving. They said the object is released. You understand? The object is what? Is released. To release something is when you are holding something, then you do what? Then you leave. When you leave that thing, you are not applying a force, you are releasing. Look at this. I'm holding this. Let me release. I just left that thing. And it is moving on its own. That is to release. When you release something, you let that particular thing move on its own. So you need to understand the meaning of releasing. It means that there is no applied force. So the free body diagram for that object is this, going to have normal force and gravitational force only. So what are the forces that can do work that are acting on that object? It's only gravitational force. Remember that normal force cannot do work because it is perpendicular to the direction of displacement. They usually ask this question that why is it that normal force does not do work? So it cannot do work because it is acting perpendicular to the direction of displacement. So let us calculate the what? Let us calculate the speed of that object at point P. So when we notice from this, we notice that work net, the total work done on an object is equal to the work done by force of gravity. Listen, this is not a formula. This is the interpretation of that particular scenario. Because the only force which is acting on that object, in that case, the force that can do it is only gravitational force. It means that the total work done, the work which is done by the total forces acting on an object, it is what? It is gravitational force, because the gravitational force is the only force acting on that object. Meaning that work done is equal to work done by gravitational force. Why? Because only gravitational force is acting on an object. There is no applied force, there is no frictional force. So work done is equal to work done by Fg. What does it mean? It means that work done by gravitational force is going to be 1 over 2 mvf squared minus 1 over 2 mvi squared. I hope you can see this, that why am I saying work done by gravitational force? Because work net is equal to work done by gravitational force. I can write work done, work net is equal to work done by gravitational force, so that someone who does not understand can see what is happening. Let me erase this, then I focus on working out the question. I'll write what I just erased now here at the top, so that we can have enough space. I hope you are understanding. Then we're going to have work net is equal to the work done by gravitational force, which is equal to 1 over 2 mvf squared minus 1 over 2 mvi squared. This is the formula that was created from that scenario. Why? The only force acting on an object is gravitational force. So okay, let us calculate the gravitational force. Lesson number 2 comes in now. Lesson number 2 is coming in. In lesson number 2, I told you work done by gravitational force alone. It was intentional. The only problem that there is in work energy and power, it is the work done by the gravitational force. I gave it to you, I told you now. You can see that we are given the height. We are given the height. So it means the height work with the gravitational force itself, not the component, not the parallel component. You understand? So we are given the height, we are not given the angle. We just move swiftly and easily. Check lesson number 2 if you do not know different method of calculating the work done by gravitational force when you are not given the incline. So it means that one, it is going to be simple. Work done by gravitational force is going to be mg, gravitational force itself, multiplied by what? By displacement, multiplied by cos theta. What is the theta that we're going to use? The object is going down. You know that when we are using the height, not the displacement, the horizontal displacement, but using the height. Theta we use is either we use 0 or 180. When the object is going down and the force is going down, there is positive work which is being done. It means that we're going to use theta as our 0. When the object is going up and the force is going down, there is negative work, you can see. It means we're going to use 180. So since the object is going down, gravitational force is always down all the time. It means there is positive work. It means we're going to have 0. Then we're going to have the mass of that object is 5 kg. 9,8 multiplied by 5. Then we have cos 0. And that will give us, it will give us what? What is the answer? Okay, so we're just going to multiply 5 multiplied by the gravitational acceleration multiplied by the height cos 0, and that is going to give us 245 joules. That is the what? The work done by gravitational force. That is 245. You can confirm 5 multiplied by 9,8 multiplied by 5 multiplied by 1. Because cos 0 is 1, it's 245 joules. So it means This 245, it is the work net, it's the total work done. It is equals to the change in the kinetic energy. So it means that if we want to calculate that one, we're going to say 245 joules is equals to 1/2 mass. We're substituting here. Then we're calculating Vf, the final velocity at P. It is the final velocity. Then the object was released, meaning that its initial velocity was what? Was 0. Let me show you. You were supposed to write 0 here, but I will write everything like this. So half multiplied by 5 multiplied by 0, everything becomes 0. So it means we're going to have 245, which is equals to 2,5 Vf squared. It's a half of 5. Then we're going to divide by 2,5. We divide by 2,5. 245 divided by 2,5, it gives us 98. Then remember, this is Vf squared, and we're not looking for Vf squared, we're looking for Vf. We have got 98 is equals to Vf squared. You understand, right? Then if we want to get V, we put the radical sign. So it means that our V is equals to our final velocity, the square root of 98, which will give us 9,9. It will give us 9,9 meters per second. Meters per second. And down. Can you see that? So it means that our velocity at point P is equal to 9,9 meters per second. We've used the work energy theorem to get that one. I hope you understood. Okay. They say that explain why the kinetic energy from P is the same as that of Q. Okay. So it is the same, the kinetic energy, because the energy is conserved from the starting point until Q. There is no non-conservative force acting on the object, so energy is conserved. Although I will explain this into detail in lesson number 4 about the principle of conservation of energy. So energy is conserved because there is no non-conservative force. Non-conservative force are forces such as friction, tension, applied force. Those are non-conservative force. They causes energy to be lost in one form or another. So energy is just going to be not lost because there is no non-conservative force. But the other questions, I will explain them into details in lesson number 4 when we are dealing with the conservation or the principle of conservation of mechanical energy. Now we'll be dealing with the work energy theorem. I think we can do another example which is displayed now on your screen. Let us do question number 6, which is being displayed on your screen. Okay. The question says that a 10 kg block is released from rest from the top of a ramp at point A at a construction site as shown in the diagram. The ramp is inclined at an angle of 80 degrees to the horizontal, and its top is at a height of 5 meters above the ground. State the principle of conservation of mechanical energy in words. I'm just going to state it, but I'm not interested in that because that's what we are going to learn in lesson number 2, which says that total mechanical energy in an isolated system is conserved. We're not interested in this mechanical. We're interested in question number 6.2. 6.2. Whereby we're going to talk about 6.2.1 and 6.2.2. We are interested in applying the work energy theorem. Okay, so 6.2 is said that the kinetic frictional force between the 20 kg block and the surface of the ramp is 30 Newton. Use energy principle to calculate the work done by the kinetic frictional force on the block, the speed of the block at B at the bottom of the ramp. I told you that the word use energy principle, you use anything which you are learning as far as energy is concerned in work energy and power. They are trying to say don't use the equations of motion, just use the energy principles. Whether you use work energy theorem, you use the conservation of mechanical energy, all those kind of formula, they fall under the energy principles. You need to take note of that. Okay. We need to calculate the work done by frictional force. The only problem that we have on the triangle is that we do not have the displacement. We don't have the distance which the frictional force acted. This is 30 degrees. This is point A. And this is point B. You can see that object which is 20 kg, it is moving from point A to point B, meaning that it is being displaced from point A to point B. In order for us to calculate the work done by frictional force, we need to calculate the distance at which the object moved when the frictional force was acting on an object. This one, since the frictional force in this case will not have any component, there is no way we can use this displacement or any other displacement because frictional force acted when an object was moving in this displacement. Meaning that in order for us to calculate the work done by gravitational force, we need to be able to calculate this displacement on this triangle. So this is very interesting. It's something that we already know. What do we have here? This is 90 degrees. We have 90 degrees. This is the displacement. This is 5. You understand? I cannot allocate this to a particular topic. This is maths. We can use sine rule or we use this. You know our Cartesian plane, whereby I remember showing you the Cartesian plane when I was showing you the components of the gravitational force. We know that this part of the triangle, we call it x because it is lying on the x-axis. This one we call it the y, and this one we call it the r, which is the hypotenuse or the longest side. So you can see that they are the same. So we know the three ratios. I remember showing you three ratios. We know that cos theta is equal to x over r, sine theta is equal to y over r, then tan theta is equal to y over x. Tan theta is equal to y over x. So we can use these three ratios. You can see we are given y. We are only left with r. Which trig ratio? We are given the theta. Can you see this is theta? Here we have theta. Which one have got y and r here? Which one have got y and r? This one, sine have got y and r. Meaning that if we want to get this distance, we can say that sine theta is equal to y over r, whereby our theta is 30. What is y? Y is 5, then we have r. Then we want to solve for r, can divide by 1. Dividing by 1 is the same as we did nothing. What we are doing here is maths. We are doing maths. Then what do we do if we want to solve for r? We just cross multiply. If we want to solve for r, we divide by sine 80. We divide by sine 80, meaning that r is equals to 5 divided by sine 80. Then r will be equals to what? That is mathematics. We use the trigonometry. And we're going to have 5 divided by sine 80. 5 divided by sine 80, and that will give us a 10. 5 divided by sine 30, it simply gives us a 10. It simply gives us a 10. So it means this distance is 10 units. That distance is 10 units. It's very important for you to be able to use this A. We just chose sine. Why do we choose sine? Because we're looking for R and we're given Y. So we're going to use something that will use Y and R. Why Y and R? Is because we're given 1. If we're given X, we're going to use the trig ratio that we have got X and R. You understand? So that we only have one unknown. Some people, they do not use this. They use what? They use the sine rule. You remember sine rule? Whereby you say that the distance, you can say that distance AB divided by sine the angle which is opposing the side which you are looking for, or the angle which is opposing the side. To oppose is to look at each other. Hey, English. To oppose is to look at each other. When you are facing each other, that is to oppose. So this angle is facing this side. So you can say sine 90, which is equals to 5. You see 5 is looking at 80, they are facing each other. So we're going to have 5 over sine 30. Then what will we have here? We're going to cross multiply. We're going to say AB. This is sine rule. AB sine 80 is equal to 5 sine 90. Then we divide by sine 80. We divide by sine 80. Then AB is equals to 5 multiplied by sine 80 divided 5 multiplied by sine 90 divided by sine 80. We know that sine 90 is going to give us a 1. You remember when I was teaching you the graphs for electrodynamic that we use sine for voltage. Okay, so we're going to have 5 multiplied by sine 90. 5 multiplied by sine 90 divided by sine 30, and still give us a 10, meaning that we can use 2 methods to calculate what we want. So we got the answer. I'm using these 2 methods so that you can choose the one you feel it is good for you. So now we know the displacement. We know that frictional force acted from A to B, and it acted and made an object to be displaced 10 units. So the displacement is 10. So if we want to calculate the work done by frictional force, which is straightforward, work done by frictional force is straightforward. We are going to say work done by frictional force is equal to frictional force multiplied by the displacement multiplied by cos theta. Remember in lesson number 1, I told you that frictional force it is going to be theta 180 because it is opposing the motion of direction. You understand, right? So frictional force is going to be, well, given the frictional force there, in the question we are told that frictional force is 30 Newton. We're going to have 30 multiplied by 10 cos 180. 80 multiplied by 10 cos 180 will give us 10 multiplied by 80 cos 180 will give us 80 multiplied by 10 cos 180 will give us negative 300. Get negative 300. So the work done by frictional force is how much? It's negative 300. Work done by frictional force is negative 300. Negative 300. So yeah. So So the work done by frictional force is negative 300. Then let us go to question number 2. Let me bring the question to at least appear again on the screen. Maybe you forgot it. Okay, you can see the question is appearing on the screen. We got the work done by the frictional force is what? Work done by frictional force is negative 300. Why are we getting a negative answer? It's because there is negative work which is being done. Energy is being removed on the system. We know that frictional force will cause energy to be removed on the system. That's why we are getting a negative answer. Okay, let us continue. It says calculate the speed of the block at point B at the bottom of a ramp. Calculate the speed of the block at point B at the bottom of the ramp. Okay, we need to calculate the speed now. We're going to use energy theorem. Look at it. We've got 30. Then here we've got 5. Here we've got 5. We've already calculated. Then we have 10. And there is a box which is 20 kg. The box was released. To be released is just that it means that the box was allowed to move on its own. The box was allowed to move on its own. That's what it means to be released is to move on your own. To be released means moving on your own. So, what are the forces that are acting on an object? We can even quickly draw a free body diagram. We have got gravitational force and we have got frictional force. Frictional force as the object is moving on a large surface. Then we have normal force. The object was released, meaning it was moving on its own. There was no force applied which caused the object to move. So we can look at it and we check what are the forces that are acting on an object that can do work. What are the forces that are acting on an object that can do work? We've got displacement, meaning that it does zero work. So it is not going to do any work, to have zero work. So let us calculate the velocity of the object at point B. That is the final velocity. What does that mean? It means work net is going to add work done by friction plus the work done by gravitational force. The object is moving down, meaning that gravitational force is doing positive work. What do we mean by positive work? The object and the force are moving in the same direction. We know that positive work is when energy is added in the system. Gravitational force is always downward, and the object was moving down. It means gravitational force is doing positive work. So let us calculate that one. I'm going to say work net, and work net is equal to the work done by frictional force plus the work done by gravitational force. Notice that this is not just a formula. This formula is specific for that scenario. Okay, for your sake, first write the formula which is general, so that you get the mark for a formula, in case you make mistake here. Then work net, it means work done by gravitational force plus the work done by frictional force, which is equal to change in K. Change in K 1/2 mvf square minus 1/2 mvi square. Then the work done by gravitational force for that object was given the height. We can use any method that we want. Check lesson number 1. Lesson number 2, if you want to understand the work done by gravitational force, if you want to know into details how to calculate it, because I dedicated lesson 2 in teaching the work done by the gravitational force only, so you will understand work done by gravitational force only. So work done by friction were already given, it is negative 300. Work done by gravitational force plus the work done by frictional force is minus 300, the one which we just calculated. The work done by gravitational force is what we want to calculate now. It is what we want to calculate now. Let us calculate work done by gravitational force, or we can calculate it on the side, or we can calculate it here. It depends. We're going to say mg, which is the magnitude of the mass and the gravitational acceleration, then we say delta y, then we say cos theta. This one is going to be minus. Then can just, before we will make any substitution, so that I'm writing in a long way so that we can understand. You can see I wrote delta y, meaning that I want to use the height. I'm going to say 20 multiplied by 9,8. What I'm holding here is the equation. 20 multiplied by 9,8. The height is 5. Then cos the object is moving in which direction? The object is moving in which direction? The object is moving downwards. Meaning that there is positive work. I'm going to use 0 minus 300 is equal to 1 over 2. M is 20. I'm calculating the velocity at B, which is the final velocity. Then the object was released. It means its initial velocity is what? Is 0. Then I need to know the work done by gravitational force. I can say 20 multiplied by 9,8 cos 0. Cos 0, which will give me 196. It means the work done by the gravitational force is 196. Did I do the right thing? 20 multiplied by 9,8 multiplied by 5 cos 0. Yeah, I did the wrong thing. 20 multiplied by 9,8. 20 multiplied by 9,8 multiplied by 5. Yes, 98. What am I doing? It was a wrong touching on the calculator. 980 cos 0 is 1. Then I'm going to have 980 minus 300 is equals to 1 over 2. Actually, 1 over 2 multiplied by 20 will give us 10. I'm going to have 10 volt square. And 980 minus 300 will give me 680, which is equals to 10 volt square. Then I divide by 10 both sides. Then 680 divided by 10 will give me 68 is equals to Vf square. I square root both sides, then final velocity is equals to the square root of 68, which will give us 8,25 meters per second down. Don't forget to write the magnitude and the direction. That is the velocity at point B. You can see how I got the work done by gravitational force. Okay, I'm just concerned about how I calculated the work done by gravitational force. It seems as if I love the work done by gravitational force when we're using a height. I want to change this one and use work done by gravitational force when I'm using displacement. This displacement, the horizontal distance moving from A to B. I want to calculate gravitational force using that information. How do I go about that one? I'm going to say, remember for work done by gravitational force I got 980, so I want to show you the other method. You can say that work done by gravitational force is equals to mg delta x, then cos theta. We've got this method. I will even give you the third method so that you choose whatever you want depending on what you are given. I'm going to say work done by gravitational force. Work done by gravitational force is equals to mass of an object, which is 20, then the gravitational acceleration, which is 9,8, then the displacement of that object, it moved 10 units. Then cos theta. What do? I told you that when an object is going down, we say 90 minus the angle of incline. Check lesson number 2, work done by gravitational force. When the object is going down, we say 90 minus angle of incline, 90 minus this angle. When the object is going up, we say 90 plus the angle of incline. You understand? That's how we move. So there we're going to have cos 90 minus 30. Is the angle of incline, is it 90 minus 30? Yes. It's 90 minus 30, then we'll have 60. Then what do we do? 20 multiplied by 9,8 multiplied by 10 multiplied by cos 60. What do we get? 98. So work done by gravitational force, still it's 98. You can see we are getting 98. We are using different methods. There is the method of calculating gravitational force. Notice that I'm using this displacement. The only thing which you can make a mistake with is the displacement. You can see here I use the height which is this height. That's why I'm using cos 0. But when you immediately use this displacement, you need to use 90 minus this theta if the object is going down. You understand? Right? If the object was going up, I was going to say 90 plus 80. Here I was going to have 120. You understand? Okay, let me show you the third method of calculating the work done by gravitational force for the scenario that is on our screen. Okay, work done by gravitational force, you can say work done by gravitational force is equal to mg, which is mg parallel, mg sine theta, then delta x cos theta. Okay, I'm going to have mass 20, gravitational acceleration 9,8. Then we're going to have sine, what is the angle of the incline, is 30, displacement is 10, then we have cos, the object is moving down, we're going to use cos 0, there's positive work. Then let us see what we'll get. We're going to have 20 multiplied by 9,8, multiplied by sine 30, multiplied by sine 30, multiplied by sine 30, and multiplied by 10, multiplied by 1. What do we get? 980. 980 joules, you see? That is the work done by gravitational force. I've shown you 3 methods. I've shown you this method of using height, this method of using this displacement, and this method of using this displacement but using the component of the gravitational force, which is the parallel component. So that's how we get to calculate the work done by gravitational force. Yeah, this was the main thing, right? We are going to calculate the work done by gravitational force because gravitational force and the frictional force, they were the only forces acting on an object. I hope you understood that and you are learning and understanding. So, ladies and gentlemen, this is the end of the lesson for work energy theorem. Please check lesson number 4 whereby we're doing the mechanical energy, conservation of mechanical energy. We talk about conservative force, non-conservative force, and many other things as we're moving toward the end of work energy theorem. If you haven't subscribed, please subscribe to this channel. This is the channel, the only channel which simplifies. It's the only channel for science that simplifies on YouTube. So please let us subscribe. Thank you.